Get ready to enter a brave new world with your host, Vasant Dar.
Have you ever wondered whether you're a video game? A game whose rules are hidden even from yourself? Perhaps you're going through life and discovering some of these rules about yourself, as are other people. But what if you're a video game that a computer is learning to play? A computer whose objective function has been specified by its designer to figure you out and press your buttons to maximize its reward, not yours. Does that sound intriguing or troubling, or both? But perhaps that isn't too far from the reality of our emerging Brave New World, where platforms discover how to play with you and play you. Joining me today is Brian Christian, author of a very interesting and timely book called The Alignment Problem. Brian describes why and how current-day AI systems are not always aligned with what we want them to do or what's good for us as individuals or as a society. It's an issue that's becoming increasingly important as machines make more and more of the decisions in our lives, from who we meet, to what information we consume, which doctor we see, and how we're judged for all kinds of things in our lives. The divergence between what we get from AI versus what we should get is what he calls the alignment problem. It's a tough problem because machines invariably behave in ways we didn't intend or expect. Brian's book also goes into some depth into the nature of intelligence, which I discussed in an earlier episode with Yann LeCun. Brian draws on animal behavior, human cognition, and machine learning to describe how intelligence arises and manifests itself. As he puts it in his book, and I'm paraphrasing, artificial intelligence puts optimization on autopilot, so we need to be very careful that we're not optimizing the wrong thing. That's what today's conversation with Brian is all about. Brian, welcome to Brave New World. I am delighted to have you on the show.
Thank you very much.
So before we get started, just tell us something about yourself, something personal that not too many people know about.
Well, I have an unusual background, so maybe that's one place to start, which is that I have this lifelong interest in both computer science and philosophy. And, it's kind of the closest thing that I have as a secular person to a religious impulse, I guess you could say, is that my whole life I have thought about these questions of just what is the nature of existence, what is the nature of human life, and whatever this says about me or how my brain is wired, it has often been computation that I've turned to for answers about these things. So what can we learn about what to order at a restaurant from studying the explore-exploit trade-off? What can we learn about, decisions in our personal lives from thinking about optimal stopping? And so that for me has been kind of this lifelong, intellectual braid between, on the one hand, philosophy, psychology, and on the other hand, computer science. And so that has really informed, obviously, the work that I've done as an adult.
So how about that? So we've got something in common there, So, as it turns out, I was very influenced by philosophers myself in graduate school in Pittsburgh in the early 80s. I had 3 roommates who were philosophers, graduate students, and they, induced me to think more broadly. They would call me, you engineer, because I was, an engineer from IIT. And, so they made me, sort of, I guess, just recognize the benefits of looking at the world sort of more broadly. And so that was that was an interesting experience. And I really got sort of deeply into it. And of course, I'd also, met my AI mentors, Herb Simon and Harry Popel. And I remember this one time I was talking to Harry, and I was talking about philosophy and epistemology, and he was nodding his head, and at some point he says to me, "You are going to write a program, aren't you?" So
I love that.
Just to be clear, right? You're going to write a program, right? So.
Yeah.
But yeah, that was a really interesting experience for me. Pittsburgh had a great department in the history and philosophy of science, so I took as many philosophy courses as I could, and I actually encourage my students to take philosophy courses. I said, if you want to really clue yourself up, take philosophy and computing, because it's important that you know the language of our future overlords.
Yes, I that's really interesting. I mean, I think these two disciplines, when I was studying, I was a double major in computer science and philosophy in the 2000s. And, at the time, that would raise a lot of eyebrows. I don't think that combination raises eyebrows today the way that it did 20 years ago or further. I think those two disciplines are on such an obvious collision course. And, I think we're seeing that now. I think computer science is this wonderful set of tools for making certain intuitions explicit. I think Richard Feynman and others have said, if you can't actually build something, then you don't truly understand it, right? So it gives us this wonderful kind of empirical framework for thinking about some of these more abstract ideas. But then conversely, philosophy gives you a way to interrogate, the assumptions that you're making when you design a model or write a program. Like what is the relationship that the ontology you've created in your program, whether it's, classic object-oriented programming where you have, these nouns and verbs that you define, is that really comprehensive of what the phenomenon you're trying to model? And the same thing, of course, in machine learning, right? Is your training data really capturing what you have in mind? Is your objective function really capturing what you have in mind? Those are sort of philosophical questions. They're about ontology. They're about metaphysics. So from my perspective, yeah, those two disciplines really have almost a symbiosis.
Indeed, yeah, and in fact, I remember even in the 80s when AI was, and by the way, AI also used to raise eyebrows. 20 years ago, people said, "Really, studying AI? You're not using these neural nets, are you?" But I recall even then the importance of actually implementing something and observing its behavior. Because that was the era of rule-based systems and production systems, and anyone who programmed those experienced the fact that they would just sort of run away from you. That the way they behaved was quite different from what you thought you'd see in their behavior. There were all these nice theories about, declarative knowledge and procedural knowledge, but when you stuck things together, you were invariably surprised. And that hasn't changed one bit, has it? I mean, we're still surprised now just by machine learning systems, so they continue to surprise us. And in some sense, I mean, this is sort of getting to, the subject of your book. We just sort of, proceed by trial and error. The machine doesn't kind of behave the way it does, so we fix it, and then it still doesn't behave, right? So we're constantly surprised by the behavior of the machines and their ability to do things that we didn't actually intend.
I think that's exactly right. Anyone who's written any amount of code, even if it's just a personal website, has experienced this, like iterative, how hard could it possibly be to express my intention, in this medium? What I want is very simple, and yet inevitably one runs into this litany of corner cases and exceptions and so forth. And I think that is the experience that, as I say, anyone would have, whether you're building, statistical models, whether you're doing HTML. But we are increasingly empowering these sorts of systems to take on ever greater roles, ever greater responsibility in society, right? Whether it is obviously self-driving cars increasingly, on our neighborhood streets. Where I live in San Francisco, I can't, walk to the mailbox without seeing a self-driving car. Or it's the way that statistical risk assessment software has become increasingly mandatory in jurisdictions all across the country and across the world. We are kind of delegating to these machine learning models the things which not only used to be done by humans, but in many cases also the things that used to be done by, traditional software of the kind of declarative if X then Y kind. And so I think that's, in some ways, the dangers that keep me up at night about AI, about machine learning, are not new. I mean, as you say, right? This is the story of anyone who's tried to program anything. But the stakes keep going up. And so I think that is the concern.
Yeah, exactly. I've spent many years building, automated decision-making systems, mostly in finance, and that's sort of given rise to sort of the more general question as to when we should trust machines with decision making because, as you say, the stakes keep going up. They keep making more and more decisions that are of increasing importance to us. I received your book as a Christmas present from my stepson who happened to be perusing it in the bookstore and said, hey, I thought this would align with your research interests. And I picked it up a month or two later and I read it and I was pleasantly surprised. So let's start with that. Like, tell us what it's about just in broad strokes before we get into some of the details and what motivated you to write it.
Sure. Yeah. So the book is called The Alignment Problem, and it is broadly about the question of how to make a machine learning system do what you want. I think that's the simplest way that I can put it. How can you, build some model that's trained by examples? How can you somehow instill the objective that you really want into that system? And how can you trust that the system has learned what you want it to have learned, or it will generalize in the way that you expect or hope it'll generalize? That's not a new problem. The framework of AI as kind of this sorcerer's apprentice situation where we could impart the wrong message unwittingly, and then the system does quote unquote what it thinks we want with disastrous consequences. That analogy and that idea goes back at least as far as MIT's Norbert Wiener, who wrote about it in 1960. But it is really now, in the era of deep learning and in the rise of these models kind of in our civic infrastructure, that we're worried about it in, I think, a very acute way. And so for me, the story of where this book came from started somewhere around 2014. So at this point, my first book had come out. I was working on my second book, and I was invited to a dinner at a Silicon Valley venture capitalist book club. And they wanted to talk about my first book, The Most Human Human, which is about the Turing test. And they invited, among other people, Elon Musk, who is very interested in AI, of course. And I didn't expect he would show up, but he did show up. And it was this very interesting moment. This was the summer of 2014. And he started kind of buttonholing everyone in the room and putting us on the hot seat and saying, give me one reason why I shouldn't be worried about AI, or one constructive thing that we're going to do to make sure that this all works out. And it was a very interesting experience for me of not feeling viscerally worried about AI at that point, but when put on the spot to articulate why, I couldn't come up with a good reason why. So that for me started this little period of cognitive dissonance.
Where, so is that, I'm sorry to interrupt here, but is that because, so I'm going back to 2014, right? So is that because at that time, the real problems of trying to get machines to be intelligent, I mean, it's it's been so hard to get machines to be even slightly intelligent, right? And we still face major challenges, right? So until a few years ago, if people asked me a question like that, I'd just sort of roll my eyes and say, look, we're barely able to build a machine that has a fraction of an intelligence of a dog. So, like, what are you talking about? Like, yeah, they're going to take over. Like, we'll figure that out.
Yeah.
But then, I remember this other event at NYU called The Future of AI, where, Stuart Russell said something to the effect there's a meteor going to hit us 60 years from now. We wouldn't say we can wait another 50 years before we address that. So that sort of struck me as, yeah, this is an important problem because we're seeing this increase. There's a palpable increase in intelligence, and it may not be of the sort we always want. In fact, many times it isn't.
Yeah.
And so that started making me take the question a lot more seriously as well. But I'm sorry to interrupt that. But
that lines up very much with my own experience, which was, for me, this question of, are computers, is AI going to destroy civilization? For me, that was a recreational topic. I thought it was an interesting topic to talk about. It was fun to talk about, but I didn't feel like palpable fear. So this was just the very beginning for me of starting to think, okay, well, I don't actually have good reasons why I shouldn't be more concerned than I am. And then over that period of time into the fall of 2014, you had Nick Bostrom's book, Superintelligence, came out. Nick was here in the Bay Area doing his book tour. And so I went out to a dinner with Nick and Stuart Russell and a bunch of people from the Machine Intelligence Research Institute. And that was kind of my first contact, particularly with Stuart, who was thinking about this as a computer scientist. I think it had been easy prior to that point for me to say, like, okay, well, Elon Musk is obviously very famous, but he's not a computer scientist. Or Stephen Hawking is a very famous scientist, but he's not a computer scientist. So for me, it was really Stuart Russell's voice kind of joining that conversation that caused me to really pause, because obviously, okay, here's someone who's one of the co-authors of the most famous textbook in the field. So he's coming from a very grounded place in the actual, technical material, and he's seemingly just as concerned. So all of that was starting to shift my thinking. At the same time, I started to see society at large through this prism. We have all these institutions in society that are essentially optimizers. We have corporations that are optimizing for various metrics of, stock price, shareholder return, et cetera. We are optimizing national economies for, GDP, et cetera. And it seems like a lot of the problems that we're experiencing in the world, from rising inequality to climate change, are essentially the result of having these objective functions, these kind of myopically defined proxy metrics for this broader kind of human flourishing that we actually care about. And those proxies are becoming decorrelated. And so in some ways, I was able to interpolate between, okay, these are the things that people like Stuart Russell are worried about, these machine learning systems that fail to capture, the designer's intent. And then we have these kind of extremely macro systems that are kind of running the world at the highest levels that are suffering from that very problem. And so it started to feel to me like, okay, well, the increasing capability of AI is concerning because it's putting more and more of this optimization process on autopilot, if you will. But in some ways, you could already diagnose the biggest problems facing humanity as alignment problems in that way. We have these numerical KPIs, and they don't capture everything that we really care about. So that was for me kind of the intellectual beginning. And then just in terms of my own life, I was still finishing my second book, and that book finished in the spring of 2016. And then what I noticed in the summer of 2016 was kind of two things. One was that the fears being expressed by Stuart and other people had begun to coalesce into an actual scientific agenda. OpenAI was founded. The Center for Human Compatible AI at Berkeley, which I'm affiliated with, was founded. There was an influential paper that had come out called Concrete Problems in AI Safety that was framing some of these kind of thought experiments that had existed in the AI safety community through the lens of, shovel-ready machine learning problems. We're worried about distribution shift. We're worried about generalization, overfitting, et cetera. And so it started to feel like an actual scientific agenda was kind of hitting the ground. And at the same time, that same summer, you were seeing things like the ProPublica series came out about the risk assessment systems that are used in the criminal justice system in the U.S., and how there are apparent racial disparities in the ways that those models are treating different defendants. And that turned into a much bigger academic conversation on how do we actually operationalize something like fairness in kind of a civil rights context. So again, it felt to me like I was starting to be able to interpolate between these different communities. You had this growing movement around issues of fairness, accountability, transparency in machine learning, this kind of present-day ethical set of concerns. And then you also had the people that are more concerned with kind of long-term safety, the sort of further in the future, higher stakes questions of existential risk and so forth. That was turning into an actual scientific agenda. And you had a generation of PhD students showing up saying, I want to do my dissertation on AI safety. So that's really where the book began for me. I wanted to try to tell the story of what I saw as the beginning of this real movement within the field.
So that's interesting. You know, you've divided your book into three parts. And first part, you say, okay, let's lay out the problem itself, the alignment problem. How are we misaligned? And that's the kind of stuff you've been talking about. And then you talk about the technology itself. And I noticed that you really sort of hang your hat on reinforcement learning and inverse reinforcement learning. And then in part three, you sort of say, okay, now what do we do about, I guess, getting more aligned or getting machines more aligned with us? So let's take things in that order. Why reinforcement learning? So just break that down for people who don't understand what it is in terms of psychology, and Skinner's experiments and however you want to state it, right? Why do you really hang your hat on that particular technology or method as being sort of critical to understanding intelligence?
I think a lot of the most present and understandable alignment issues, whether it is facial recognition systems that can't identify, dark-skinned faces, or, risk assessment algorithms that have disparate impact on people from different, protected classes, those are all sort of within this paradigm of supervised learning, right? You just have this labeled data set and your system learns to make these predictions. I think it felt to me that for a lot of people, even who already sympathized with those problems, they couldn't necessarily make the leap to imagining a system that actually had agency to do stuff in the world. And so for me, I wanted to talk about reinforcement learning as a way to ground this public conversation about the longer term risks in an actual technical foundation. So part of what I wanted to do was just pedagogical. I wanted to enable a broad audience of people to understand what the people who are thinking about reinforcement learning systems, how do they work? What are the ways that they can go wrong? What are the techniques for trying to prevent them from going wrong? So that's probably my number one motivation. There is a conception that a lot of people have that machine learning systems aren't to be particularly worried about because they don't do things, they only make predictions. And I think that's not true. And so I wanted to explore the notion of systems that actually have quote unquote agency or can sort of take actions. There's also, I think, very, very profound parallels between reinforcement learning and human cognition, which is you've touched on a little bit in your question. Reinforcement learning kind of broadly grows out of the behaviorist tradition in the early 20th century. It has this wonderful moment in the 1990s where this model that was developed in the reinforcement learning community called temporal difference learning ends up supplying an answer to this open question in neuroscience, which is what's the role of the dopamine system in the brain? And so, we had all this neurophysiological data saying, okay, the dopamine has some connection to reward, but it's not literally reward. It has some connection to surprise, but it's not literally surprise. What the heck is this system built to do? And to make a long story short, when those data came across the desk of Peter Dayan at the Salk Institute, who had done a lot of kind of foundational work in reinforcement learning, he immediately recognized it as like, oh, the brain has a temporal difference learning system. This dopamine spike is a TD error. And so for me, that is a very profound example of
By
this
TD
idea.
error, you mean there's a difference between sort of the previous state of the world and now your new expectation.
That's right.
Okay.
That's right. You are. It's an error correction code essentially that you've updated your prediction about something.
Right. Yeah.
For me, that's a very powerful clue that the project of artificial intelligence is in this way recapitulating some of the same mechanisms that were discovered by evolution. That, depending on who you talk to, it's believed that some kind of TD learning mechanism evolved independently in mammals, in humans, in bees, in different organisms, kind of a number of different times, a number of different independent paths. And so this is something that evolution has found several times. This is the same thing that we've found now computationally. To me, I take that as a sign that the project of AI has started to hit what I think of as like the philosophical pay dirt. We're not merely developing tools that, solve practical problems from an engineering perspective, but that we're actually kind of understanding the nature of intelligence itself. And so for me, reinforcement learning is very powerful in that way, because I think it really bridges between human cognition and animal cognition and AI.
Yeah, no, it's interesting because reinforcement learning has come up like a few times with two of my guests, Molly Crockett, who's a neuropsychologist at Yale, and Jonathan Haidt, one of my colleagues here at NYU, who's a social psychologist and a moral philosopher. It's interesting because they both allude to sort of reinforcement learning as Jonathan Haidt, for example, talks about why has teen depression in girls gone up relative to boys. He sort of traces this back from the emergence of Facebook and the like button, and then Twitter introducing the retweet button and all of that. And it's an intriguing theory that he has that explains phenomena that we're seeing in society in terms of reinforcement learning, right? Just this expectation that you have of people saying, yeah, I like this, and as long as it keeps arriving, you're kind of okay. And then it doesn't, and then it's a crash. It's almost like cocaine or something like that. You have this expectation that the world is going to be great, and then it sort of doesn't pan out that way, and that sort of leads to a crash. So it's interesting that we're seeing this sort of paradigm emerge, not just in sort of hardcore AI as a mechanism for intelligence, but just also something sort of that explains phenomena that we're seeing in society.
Yeah. I think reinforcement learning is, to an underappreciated extent, already being used by social media companies. For example, at Facebook used to organize their notifications and their newsfeed using supervised learning. So they would just build this predictive model that, for every piece of content, what is the probability that you would interact with this piece of content? And so if that probability is over some threshold, then we'll push a notification to you, or we'll sort your newsfeed in descending order by that metric. This has gotten, circa 2018, replaced with a reinforcement learning model in which your interactions with the system are treated as like points in this video game that Facebook is trying to play. And so Facebook now takes these temporal contingencies into account. So if they send you too many notifications, you turn off notifications altogether, and that's essentially equivalent to game over in an Atari game. And they're literally using DeepQ networks, which is the model that DeepMind built to play these Atari games. Facebook is literally using that exact same architecture to make decisions about push notifications on mobile devices. And so I think there is something very intriguing about the way in which we talk about gamification of these platforms, but we don't necessarily appreciate that from the platform's perspective, we are the video game that they are playing. Very quite literally.
Oh, that's a good one. I hadn't heard that. Fascinating. Right. So each of us is a video game.
Yes.
A unique video game. Wow, I hadn't thought about it that way. It's just very, very interesting.
The other connection I would make just on this topic of reinforcement learning is that I think once you establish that there are these kind of fundamental links between machine learning, cognitive science, animal behavior, you get to bring a lot of insights over that kind of bridge in both directions. So, one of the things that I talk about in the book is the way that incentive design in reinforcement learning is extremely, extremely difficult. There are many anecdotes of researchers trying to add some kind of incentive to a reinforcement learning system, and it goes totally off the rails. And in parallel, I give examples of corporate settings where an incentive causes a company to go, off the rails, or examples in parenting where you give a certain incentive to your children to behave a certain way, but they exploit it ruthlessly. They find some loophole. And so that's another way in which I think these parallels are, they're more than metaphorical. And I think they give us an opportunity to hopefully borrow a little bit of insight from other older fields that have been dealing with some of these issues longer.
Fascinating. So let's turn to a couple of other things that you've talked about, things like bias and fairness. And, you referred to like the compass system. It's interesting. When I read all that literature, I was thinking to myself, like, was this really biased? There's a lot of attention being played to racial issues and stuff like that. So that certainly gets people's attention. But to be honest, when I looked at sort of both sides of it, I was like, I don't know. I mean, one could make the case that the system is biased, but then on the other hand, North Point says that our systems are well calibrated. And so there isn't actually any racial bias from that standpoint. Mm-hmm. But then I guess the ProPublica people were focusing on other measures of fairness, right? And then you have this paper by Manish Raghavan and John Kleinberg and Sendhil Mullainathan that shows that you're never going to have a system that satisfies everyone. It's except in very special cases that just isn't going to happen. So, let's just go back to that whole compass thing and parole decisions. Yeah. What do you think? To me, actually, when I read your book, it seemed like there was more of a case for gender bias than racial bias, if anything, right?
Mm-hmm. Yes. Sam Corbett Davies at Stanford, for example, found that compass, while it is what's called calibrated with respect to race, it's not calibrated with respect to gender. And so there's a whole separate argument that one could make there. Mm-hmm. Yeah, it was a very interesting experience for me going into that literature and, interacting with that research community, because I think my experience of kind of going further and further into that topic was one of, in a way, being less certain as I went on that I understood what the story really was, right? So I, like many people, read this ProPublica article, which got very widely shared kind of within the academic community, and thought, oh, wow, this is like a smoking gun. And the further you go into it, the less clear it is what's really going on. Is calibration the best metric among, a bunch of trade-offs that you have to make? You can define a bunch of these desiderata that all seem really good, and they all seem like part of our intuition of what it means to operationalize something like fairness. So, just to kind of unpack for people, calibration is the idea that a defendant who's rated an 8 out of 10 on this risk scale has the same probability of being rearrested as someone else who's an 8 out of 10, regardless of what racial group they belong to. Well, that sounds pretty desirable, and 8 out of 10 means 8 out of 10. It doesn't mean one thing if you're white and another thing if you're black. So that seems pretty desirable. The other thing, which is what ProPublica focused on, is the rate of false positives to false negatives. So given that you are a black defendant who has been miscategorized by this model, are you more likely to have been a false positive or a false negative? And here you see huge disparities between white and black defendants.
Mm-hmm. So much higher false positive rates than black defendants.
Yes, mm-hmm. And much higher false negative rates for white defendants.
Right.
And, one of the things I found interesting here is that there's a case to be made that I think one of the biggest things that's going wrong with these models is that we talk about them oftentimes in a kind of shorthand as if they are quote-unquote risk prediction models or crime prediction models. But we can't observe crime. We can only observe arrests and convictions. And so there are data that I cite in the book showing that in Manhattan, for example, black and white Manhattanites self-report the use of marijuana at the same rate, same proportion of people, use marijuana. But black Manhattanites are, if I'm remembering the statistic correctly, 15 times as likely to be arrested for the use of marijuana. And so even if you have this model, which is this perfect oracle, you're still not measuring crime. You're measuring arrest. And that's already this huge problem. So I think there are many kind of interlocking issues that are going on with these criminal risk models. But for me, that's one of them that's paramount, is this question of, is the thing we're trying to predict really the thing that we care about in this case?
So talking about predicting what we care about, like prevention, I wonder whether some of the existing problems we care about in justice, insurance, and a bunch of other areas will get solved because technology will make things that we care about more easily observable and enforceable. So, for example, at the moment, we assume that a defendant is not observable once bail is granted. But what if technology makes it possible to give the defendant the choice of being observed instead of incarcerated? So in other words, new kinds of intervention become possible with technology, which changes what you should be trying to predict. I see the same phenomenon in insurance, where some laws, such as no fault, are based on outdated assumptions about the lack of data. Whereas with vehicles equipped with cameras and other kinds of sensors, fault should be directly observable. So I wonder whether tech will eliminate this kind of noise in areas such as criminal justice and insurance, albeit at the expense of privacy.
Yeah, I mean, I think you're highlighting what may be coming for us in the coming years, which is kind of a potential fairness-privacy trade-off, where, you know, we'll have some policy decisions to make about, okay, well, if we can track people in this way, then maybe that can alleviate some harms in the fairness arena, but it's imposing harms in the privacy arena. And so, I mean, I think these are the kinds of trade-offs that at a certain point become, you know, inevitable and become just political conversations. I do think that people's understanding of these criminal risk assessment models is beginning to evolve. I mean, another level of this is that these models often make predictions about rearrest and separate predictions about failure to appear in court. Now, some models conflate those into a single prediction, which I think is a huge mistake. But if you treat them as separate predictions, you're still left with a huge societal question. Let's say, for example, you predict someone as a high, quote-unquote, risk of failing to appear for their court date. You have a huge latitude of things that you can do in response to that prediction. You can incarcerate the person, which is what typically happens. That's one way. I would say that's the most brute force way of ensuring that they appear for their court appointment. But you could also send them a reminder over SMS. And there's a lot of research that's coming out suggesting that that is actually rather effective. And so I think there's this other gap, too, between the prediction and the actual intervention. And so that gap ends up, I think, being extremely significant. And that's not necessarily one that we talk about as often because it's not part of the modeling process per se. But I think it's vitally important to think about how the prediction hands off in terms of an actual intervention. I mean, another example here, there was a study done by the Rand Institute, or the Rand Corporation, about predictive policing in Chicago. The Chicago Police Department built a model that predicted that a certain group of about 1,000 people were at a 100x risk of being homicide victims, of being killed. And this model was accurate, but even if you're at a 100x risk, homicide is so rare that it's still like 1 in 1,000 people or something like that, or a couple out of 1,000 people. And this was a case where the Chicago Police Department had this model. The model was accurate, but they could never figure out how to translate those predictions into an intervention that would make the people safer. It's like, what do? Do you go around to those 1,000 people and just tell them, like, be careful? Like, what do you do? And so I think that's, again, like this gap from the quote-unquote accuracy of the model and what we're supposed to, what change it's supposed to affect in the world, I think is a kind of surprisingly non-obvious.
Yes. In fact, what you care about most often is intervention. Even in these parole decisions, what you want to do is you want to be fair. You want the person to show up, and so maybe the intervention decision is, we'll let you go, but we'll track you because we want to be fair to you, but at the same time, we don't want to make mistakes. So I agree. It's sort of the intervention that we're very often most concerned about.
The intervention gives us a starting point for thinking about, whether we're more concerned with false positives or false negatives, right? Like in the case of just sending someone an SMS reminder, the cost of a false positive is like, 1/10 of a cent. You've just sent an unnecessary SMS. Oh, well. But if the intervention is that you're incarcerating the person, that's a huge deal. So that's another funny thing, is that the interventions kind of reflect back on the modeler what sorts of fairness criteria are worth thinking about, even though the intervention is kind of quote unquote outside of the model, outside of the prediction itself. So I think a lot of these things are really happening at the membrane, if you will, between what we consider the data science part and what we consider the policy part. That you can't decide in a vacuum what the appropriate kind of fairness desideratum is unless you know what at a policy level is going to happen as a result of that prediction.
Right. So let's, I guess, touch on a related issue of bias. And you've quoted someone who, in the context of all these systems that learn from all of the data out there, and they're learning the bias that's in the data. And someone said, trying to debias data is like putting lipstick on a pig. So then is it the role of the algorithm to create an unbiased model from the biased data? It seems to me that this should be possible by specifying the desired outcomes from the system and then just living with the fact that these might be suboptimal in other ways, that the system will make other kinds of mistakes in its quest to mitigate bias. How do you think about this?
I think there are things that one can do. The computer science community, there are a lot of people asking this question of, what do you do when you have less data about a certain subgroup in a population? Do you undersample the majority population in your training data? Do you oversample the minority group in the population? Do you build two separate classifiers, one trained on each group separately? Do you, create some generative model that's going to give you synthetic data and augment your data that way? This is a very active area, and I know a lot of people, are working on this as we speak. I think one of the especially tricky aspects to this problem in a lot of domains, and I think finance is actually one of these domains, is that the data that you see is a result of the models that are being used. So, there's this book called An Engine, Not a Camera, which looks at, financial models. And there's this funny thing, for example, with the Black-Scholes equation for option pricing, where it's initially developed as a descriptive model. Like this appears to show how people are pricing options, empirically. But then it gets adopted as like the de facto standard way for pricing options. I think there's things like this that happen, and finance, again, because so much of finance is driven by models, you can get these weird feedback loops. And there are kind of potential ethical issues here. So if there's a population that you don't have a lot of data about, let's say you're doing lending, you don't have a lot of information about some subpopulation, and so you're going to necessarily make less accurate decisions about who's creditworthy. And because you're making less accurate decisions, you're going to perceive the creditworthiness of that population as lower. But not because of population, it's because of your model. But your model is now sort of stuck in this feedback loop where it's learning from its own mistakes.
So in your words, it doesn't have the curiosity to explore and find out more about the population on which it has less data.
Right. And it's sort of at some level failing to recognize that its own model is a big part of the phenomenon that it's observing.
Right. That's an interesting observation because I agree that sometimes the data is an artifact of the model that's used, and other times it may not be. So financial markets on their own, they sort of that's how they work. They're not really being necessarily impacted by specific models. Although I sort of, as I say that, I wonder whether that's true, considering the sort of recent phenomena of retail trading and how that's altering the dynamics of markets. But this, I agree. This is like a fascinating question and one that I've been fairly deeply involved in, just from the standpoint of trying to build systems that somehow take care of this bias.
Mm-hmm.
So yeah, for me, it's a very interesting general question as to how you can, I guess, put the bias in the algorithm in a way that sort of rewards the behavior that you want, and so you can get the machine to actually learn what you want. And you allude to this in your book as well, that reward the things you want to see in reward states as opposed to actions, is, I guess, the way you put it.
Right. You get this. I mean, this gets back to kind of institutional incentive design. So one of the examples I give is, my friend and colleague Tom Griffiths, who is a computational cognitive scientist at Princeton. He's also a dad, and his youngest daughter was cleaning up some food that was sort of crumbs that were on the ground. She swept it up and put it in the trash can. And he said, "Oh, wow, great job. You did a really good job sweeping." And then his daughter dumped out the trash can on the ground again in order to sweep it up a second time and get a second heaping of praise. And this is such a classic thing that you see in reinforcement learning. Yeah. There are echoes of this everywhere. There was a group of grad students from Stanford building a soccer playing robot, and they gave the robot small incentive every time it took possession of the ball. But the robot learned that it's easier to just vibrate its paddle against the ball than it is to actually play soccer. So it just tried to get an infinite number of quote-unquote possessions. And this gets back to insight that you were describing, which is that fundamentally we need to reward states of the world, not behaviors of the agent, right? So if Tom, as a dad, instead of saying "good job sweeping," if he said, "Oh, look how clean the floor is," that sort of closes the loophole, so to speak, right? And so I think that's just one of many examples where you can see these kind of lovely and I think profound echoes from the human side to the AI side.
Human intelligence is very subtle. It reminds me of this animal scientist called Temple Grandin.
Yes.
There's a book by Oliver Sacks, an anthropologist on Mars, where there's like 7 fascinating case studies, including Temple Grandin's. And I mean, she talks about how human cues are just so subtle and complex, and that there's all manner of information in them that machines just don't have a clue as to what that is. Which gets me to sort of the hard question that your book tries to address, which is, what do we do about this all, right? I mean, here we are trying to align the machine with us, but we don't even understand who we are and what we want. And there's 2 parts to this question. I'll save the second part for a little bit later. But what hope do we have of actually accomplishing something like that, where we are unclear as to what we even want, right? So what are we going to align the machine with?
Yeah, so, I mean, this is a huge question. This is the question in some ways. I think as a starting point, there are a number of methodologies that have been developed for somehow getting this information into the system. So one of them is to handwrite an objective function. But this is extremely brittle. It's very error prone. And
myopic, as you pointed out earlier. Yeah.
Yes. So there's kind of this push for, is there another way? Is there a better way? The simplest is what's called behavior cloning, or sometimes imitation learning, where instead of specifying what we want, we just allow our own behavior to be observed. We just demonstrate something, and we tell the system, do it like this. Do it the way I'm doing it. The canonical case here, the case study here is self-driving cars. So some of the earliest actual work on self-driving cars on real highways goes back to the early 90s. This was at a time when they couldn't possibly model the trajectories of other cars. They couldn't really model the dynamics of the physics of, what happens when I turn the wheel? What's this going to do to my own trajectory? All of these things were kind of computationally infeasible at the time. But what they could do is say, we're going to slap a camera on the front of the car. It's going to take grainy photos of the road in front of us, the lines on the road. And we're going to treat it like a supervised learning problem where you're just going to learn to map, the rotational angle of the steering wheel that the human, is inputting to what you see on the road. And then once you've collected enough data on how you map these kind of lines on the road to steering wheel angles, then we're just going to hit the button and let you drive how you think a human would drive in that situation. And now this is a bit of a hack, but it works surprisingly well in a number of domains. So that's one approach, right? This idea of we'll demonstrate it. And you can augment that in certain domains. So this gets us into what's called inverse reinforcement learning, where instead of directly modeling your behavior, the system makes inferences about what it thinks you're trying to do based on the actions that you're taking. So even if you can't execute something perfectly, if you can get it in the ballpark, the system ideally can realize, oh, okay, this is what you're attempting to do. And the system may be able to do that at a higher level of proficiency than the actual human demonstrator. So this, the famous example of this is the Stanford helicopter that can do all these insane backflips and things like that, including tricks that humans can't execute, perfectly. For me, there is reason to feel hopeful in this area. One of my favorite studies was in 2017. There was a collaboration between DeepMind and OpenAI on a question of whether you could train a reinforcement learning system that was controlling this little robot to do a backflip. And I think this is such a perfect little case study because all of us know what a backflip is, but it would be very difficult to write an objective function that specified what a backflip is as a function of the torques on the joints or the rotational velocity or this, that, and the other thing. I mean, maybe you could do it, but it would take forever and it would be probably pretty brittle. On the other hand, you can't really demonstrate a backflip either. It's hard for people to do it. It's also, even if you had a robot and you had a joystick, it's hard to do it on the robot. So, okay, what do you do when you can't articulate the reward function, numerically, and you can't demonstrate it? Well, it turns out that you can just have the robot demonstrate pairs of behaviors, initially at random, and ask you which of these is closer to the thing you want me to do, which is like epsilon closer to looking like a backflip. And it turns out that after about 900 of these comparisons, which takes about an hour, it's very tedious, but on the other hand, 900 bits of information is very little, the robot figures it out. And it can do these kind of beautiful, gymnastically perfect backflips just based on you having clicked, which of these two videos, is closer to the thing that you want. That to me is like about the most hopeful that I've felt in the context of AI safety, that we are starting to build a set of techniques that enable us to extract, if you will, these kind of human concepts, somehow get that out of the brains of people and into this actual system, right? So the backflip represents this kind of very complex, nonlinear, aesthetic preference that people have. And here's a method for somehow getting that out of a human's brain into the reward function of a reinforcement learning system. I think it's very, very remarkable. I think it's, for me, very hopeful. I have no illusions about how difficult it's going to be to actually scale this up. I'm not naive about that. But I think just as a proof of concept, there's something for me very hopeful there.
That's fascinating. As you were talking, I was thinking about situations where we want imitation and where we don't. So it seems to me that for problems involving perception, like driving or translating language and other common sense kinds of things, imitation seems like the way to go to make machines smarter. But when I think about imitation involving societal things, where historically humans have a bad track record, that's probably where we don't want machines to learn through imitation. Imagine machines imitating the morality of human behavior in the 18th century. Not a pretty picture.
From my perspective, even if we quote unquote solve the alignment problem, meaning we can develop these arbitrarily powerful systems that do what we intend, what we mean, what we desire, there's still, I think, to your question, a very real risk of putting human civilization on autopilot and locking in our values and beliefs at this kind of not fully mature stage, right? So, you shudder to think what it would have been like to lock in the morality of slavery, for example, right? Or,
right.
Take your pick, like whichever century, if they had AGI then and they could just sort of lock their values in, and who's they in this case is also the obvious political question. But that would be, from our perspective, centuries hence, that would be a disaster, even if it would be quote unquote aligned with the people who, set it in motion. So I think that does suggest to us that this value of remaining uncertain, I think, is incredibly important, in part because future people's values are going to differ from present people's values. And I think that's a natural part of, how society kind of evolves. There's also a question of how might we get beyond imitation in terms of the things that we don't consider ourselves particularly good at. And so, there's a researcher named Paul Christiano who has this idea that he calls iterated amplification. And it's this idea that you train a model to essentially inform a human decision maker so that the human decision maker becomes empowered to make a better quality decision than they could have on their own. But then the model learns to predict the decisions of this empowered human or augmented human. And in so doing, it becomes a better tool to empower people to make even better decisions, and then it can model those even better decisions. And this sounds a little bit pie in the sky or something when I articulate it that way, but this is exactly how systems like AlphaZero work for playing Go. So AlphaZero has what's called a policy network, which generates a probability distribution over all possible moves. And then it can do what's called a Monte Carlo tree search, where it actually explores the game tree, applies heuristics to evaluate future board states and backs that up. And essentially the way that it works is that the policy network is trained to predict the decisions that the model itself will make after having explored this huge tree. So it's learning to imitate an augmented version of itself. For me, this is the flicker of hope. We have the beginnings of these methodologies for trying to kind of transcend, for lack of a better word, these limitations that we have while staying, in the driver's seat. That's the idea. Again, how does that scale up to the entire criminal justice system? I think is a question for us in the coming decades. But I see kind of this flicker of how we might start to think about a problem like that.
Well, Brian, it's been a fascinating conversation. I've learned something. So thanks so much for sharing your thoughts. I certainly enjoyed reading your book, and I'm sure that our listeners will as well. So thanks so much for that.
I appreciate that. Pleasure is mutual.
I think your book raises some really important and timely questions. We are far from sort of answers to these, but I think the fact that you've stated them so clearly is wonderful. So thank you for that.
Yeah, it's my pleasure. Thank you.
All right. Take care, Brian.
Bye.